I'm gonna talk about past stuff that so it's past mistakes, stuff that I knew incorrect and that I'm now correcting now because I learned about it. Um, for example, let's go to the first one. The first one is supersonic shock intakes. Now, I put a video when I went to the museum where I saw the SR-71 Blackbird plane. And when I went there at that time, I had like a not full understanding, not even a very good understanding, but I have some idea of why supersonic shock intakes were made. It's just I didn't really understand what they were doing to the air to make them work. And before I even went to the museum, I kind of sort of try to figure it out. But then when I went to the museum, I really wanted to figure it out. Now, what I thought at the museum was that I think I have an image. So let's show it with an image. No, you know what? Actually, I am gonna draw it. I think drawing it is gonna be a little bit. It's gonna be a little bit easier to understand. So, what I thought happened was that when you had the shock intake and the engine on the side, and here the engine starts, what I thought happened was this. I thought that the shock waves met in the middle from, so this is the cowl flap. I thought the shock waves were gonna meet in the middle and that was gonna compress the air to force it to compress here and here so that you would have more air coming into the engine. But, so this is what I thought happened, but this is wrong. And this is wrong for one reason. When you start going at really, really high speeds, you don't need the entire intake to work because it has too much air, especially when you go more than Mach 2 or Mach 3. So let's imagine it this way. If you have an engine with the full nozzle open, it's gonna have all this cross section of air mass going into the engine. But when you go supersonic, this mass inside is gonna be at slower speed than the air going outside. So outside is gonna have a larger speed vector and inside is gonna have a smaller one just because the engine doesn't breathe that much air, doesn't function that way. And what happens when this specific scenario happens, the entire engine cross section is gonna have a bow shock. So basically the entire engine is gonna act like a massive body inducing drag. And that is one of the main reasons that you have a movable cone that blocks a certain part of the intake. Because basically what you do is you block almost the entire section of the intake and you just leave these pieces behind. Now that is one of the reasons. But one thing that I understood wrong is this one. In reality, you don't want to compress both of the shocks inside for two reasons. One is heat. Going supersonic causes a lot of heat, and heat is something that you need to manage. Now, if you force two shock waves into a confined space, heat is going to become even more of a problem. So you don't want that. In reality, you want the shock to be on the outside and have slow, still air all behind the shock wave, right next to the engine. That is one reason. One is heat. And the second one is, as I said, when you go supersonic, you don't really need the entire air mass going into the engine, because your engine is not going to be able to breathe at the same speed as the plane is going. Now, because of this, the aerodynamic, how it happens a lot differently. And I'm going to show you a picture. So for example, which picture should I show? Let's show this ones. So this is the cross section of a cone shock intake. Now, if you see carefully here, the shock wave, it's actually on the exterior part of the cowl flap. And that is done precisely so that you miss most of the compressed air, and most of the compressed air is outside of the engine cross section pretty much. And inside, what you get, it's a different gradient of less compressed moving air. Now, when the shockwave passes a mass of air, it is gonna impart per se a slower, a small like movement into the air. Like, so in theory, when a wave passes through a medium, the medium doesn't actually move. Almost all of the wave just passes without moving the medium. That's what happens mostly in water. But when a plane is going supersonic, the shock wave does actually, and not just the shock wave, but the entire mass of the plane, it is going to impart a small forward movement of the air in front of the shock wave. It is very small, and it is most noticeable right before the shock wave. Like, not a big distance behind the shock wave, but no, it is most noticeable like right behind the shock wave. And that's why, one of the reasons why the shock wave is really close to the cowl flap. Now, why does this happen? Because you want a laminar flow going into the engine. And to achieve that, what happens is that there's something called a Mach number that you have to calculate in computers to a very specific speed and cowl flap and shock intake configuration. So more or less you can get a visual idea of if the plane, this would be the front part of the plane. Now the shock wave starts here. Most of the air, the high pressure air, it's gonna come outside of the cowl flap, and then the cowl flap is gonna impart a second shock wave, but because of the angles, is gonna have a more laminar flow going into the engine. Now, it is very hard to explain for me without diving a little bit deeper. So I think I'm just gonna nod. But I learned this, and it is very different to how I thought it worked. Like, it doesn't really work the way I thought it would. So that was my first mistake that I did, and that was when I made a video on the museum. So this is the actual mechanism of how it works and why they are designed this way. Now, this is the first one. The second mistake, quite a big one. Actually, this one, it's a little bit more interesting for me because I talked about it with people, and people had a misunderstanding too of how exactly it worked. But now I learned the correct mechanism of how it works. And that one is electrical grid on the United States. The United States, to be completely like factual, I am gonna say it first. The United States, mostly for residential purposes, has a 240 volt single phase electric power coming into a residential home. Now, the energy supplier doesn't use single phase 240 volt. The energy supplier uses something more like triple phase 480 or more volts, 400, 500, 600, 700. Now, what happens with the triple phase 500 volt to come to single phase 240 and eventually to single phase 120? That is what you get on most outlets. So let's start with this one. On the video I mentioned that you could hook up two terminals of your breaker box, and because the waves were opposite, you matched them and you were gonna get 240 volts from a two-phase 120. So exactly what I said, I think was this. I said that the power that you got on your breaker box was 120 two-phase, and they were mismatched in a way so that when you connected positive to negative of the other phase, you were gonna get 240 volts. Now, this is completely wrong because first, that's not actually how it works. Second, it wouldn't actually work because most of the time, if you did something like that, most of the time you wouldn't get 240 volts. And second, on electricity, you cannot really connect one phase to another phase and expect it not to interfere and add up perfectly to double the amount. So it doesn't work of you connecting on electrical stuff. You cannot connect 120 volt terminal of some phase to 120 volt of another phase terminal, even if the phase is completely mismatched. You cannot actually connect those two and get anywhere near 240 volts. That's just not gonna happen. It's not how it works. How the American grid works is the supplier has the very high voltage three-phase power coming from the grid. Now, this triple phase on the transformers gets separated into single phase. Now, the single phase, it's separated so that it's always 240 volts. But they don't send you So it's always separated in a way that it's 240 volts single phase, and every single phase 240 volts is gonna be added up in a transformer to make the triple phase current going through the wires on the grid. But coming back to residential power, on the residential side, you have 240 volts single phase, and what they do to provide you 120 volts on the outlet is on the transformer. So the transformer has a coil, and the coil has the 240 single phase on the entire coil. And what they do is they put a wire on the middle of the coil so that you get two phase 120 volts from one single coil of single phase 240 volts. So you get two phase 120, but in reality is not like mismatching terminals, is just in reality a single positive and a single negative from a single coil that's 240 volts. That's how it works. And that when I made the video about the power stuff, I didn't know the correct way it worked, and I learned it like maybe a couple of weeks ago. And it is a very important distinction because you know, every country has it different. Like I know Europe has it different. The person that first made me realize that I knew it wrong was someone from like Singapore or something like that. And in Singapore, they have a different grid too. It operates in a very different way. Um, and there was one more. I remember it was three mistakes I knew. Ah, the last one. This one, I didn't really talked about it on a video, or I really talked about it with anyone. But if you know me, and if you watch the previous videos I made, you know that I like geometry, and I like making stuff and how the shape of things make it so that they interact on certain ways. One of the examples that I gave was with tire angling. And I said that cars were inherently stable because of the angle of how the tires touched the ground. And that applies to motorcycles. That's especially the case on motorcycles. I think I was talking about, it was something about tires or planes. I don't remember. But trains. So now the mistake. Most people know, and I learned it like on YouTube and like on some papers, that the wheels of a train are conical shaped. So they're like this. This is how the train tires look. And here's the axle, and on the other side. So they're kind of conical. The train well, not the train tires, the train wheels. And here's the I-beam for the tracks and the middle connecting structure with the bolts going down. Most people have seen these, and there is a very simple explanation for this one. The circumference on the inside is bigger than the circumference on the outside. That is just very easy to see by just looking at the shape. Now also, most people know that the reason why this is done is because when you take a corner, right, on the track, the circumference on the outside of the track, it's bigger than the circumference on the inside. Now what they say is that when a train takes a corner, this is naturally stable because when it takes a corner, the bigger track, it's gonna be on the outside track, and the smaller track, it's gonna be on the inside. And just because of how geometry works, on the outside, this part of the wheel is gonna be touching, and on the inside, this part of the wheel is gonna be touching. So the entire train, instead of sitting on the middle, basically just moves a little bit into this side. And so this is touching the track, and this part is going to be touching the track. Most people have seen that, me included. But, and here's the thing. I thought this was inherently stable. And I thought that for many years. I thought trains would naturally go on a perfectly straight track, perfectly straight, because of this. But this is wrong. On a straight track, this actually makes it worse. Why? Because think of it this way. If you have a cart and the cart has 4 wheels on each corner, right? Just imagine for a second, and the tracks are perfectly, straight, completely parallel to the vehicle. Now, imagine the vehicle sort of tilts one way. Well, if the vehicle tilts a little bit one way on a completely straight track, then there's going to be a diagonal mismatch of the tires. This tire, the bigger circumference is going to touch the track, so it's going to want to pull forward. This tire, the smaller circumference, is going to want to touch the track, so this one is going to pull down. On this side, the bigger circumference is going to want to pull forward, and on this side, on this side, the smaller one is going to try to pull back the car, and on this one, the bigger part of the wheel is going to touch, and is going to push the car. So once the car tilts, just because of how the forces interact, it is actually not going to want to tilt and stay there. It's going to actually tilt and then tilt the other way. And then when you're in this position, it's just going to want to tilt this way and back and forward and back and forward. Now, you can draw it yourself and think about it for like 2 minutes, and you're going to understand exactly what I'm saying. It's just when you actually start thinking about the circumference of the wheels touching the track on a perfectly straight track, it sort of doesn't make sense. And I thought that it would have made sense. I thought it was going to just balance itself out when the vehicle tilted sideways or tilted like this, because the train can tilt on this axis and also on this axis. So in reality, it's going to tilt more like this and then like this and stuff like that. And what I learned was that high-speed train suspension has to account for the train oscillating and vibrating because of the inherent instability that the conical tires make. So when I learned it, I was very shocked, because for many years I thought that the conical shape on the train wheels only served to make the train more stable. But that's wrong. That's not a correct thought. Conical shaped wheels on a train really only benefit the train when going on a corner. But when going straight, the inherent conical shape and the inherent not perfect alignment of the train with the track makes it so that the train is gonna wanna move, and at very high speeds the train is actually gonna vibrate and oscillate. And when harmonics come into play, when with very big stuff, you can actually damage stuff and things can go bad. And one of the examples of this is the Japanese Shinkansen train. The Japanese Shinkansen train actually uses a smaller angle than standard on its gauge precisely because of the oscillations. And that's one of the things they had to take into account because, yeah, I mean, conical shape on the wheels helps the train keep itself on the rails and helps the train with cornering. But, you know, on high speed, the vibrations can become a real issue. So, Shinkansen train is one of the examples that I can find online of where this train wheel geometry affects the train, and actually we went a little bit backwards and made them a little bit less conical because of the vibrations. um, and those are three things that I learned, that I corrected myself, that I my understanding of it before was wrong. Two of these, the supersonic shock intakes and the electric power grid, those two I actually made a video, so that's just a full correction. And the Shinkansen train was something that I knew before, that I learned like a couple of months ago, that got corrected. um, that's pretty cool. It's pretty enjoyable. um, I think that's it for today.